to yet another class, and I'm Dr. B. Today we are going to look at how we can determine the half-life equation for the zeroth order. So remember that earlier before now we had discussed how we can be able to derive the zeroth order rate law and calculate graphically also the rate constant for a zeroth order. Today we are going to look at how we can be able to determine the half-life for a zeroth order. So let us say today we are going to look at the half-life for what? A zeroth order. A zeroth order. Now look at the half-life for a zeroth order, but the question in there is, what is half-life? What is half-life? Now we grow to understand the fact that half-life simply explains the possibility of the concentration of a reactant to go half of its original concentration. Two things are involved here we must understand. It is not about the mass of the reactant, but the concentration. Usually we wrongly define this as the possibility of a substance to reduce to half its original size, but that is not too correct. It is the possibility of the concentration of a reactant or a substance to reduce to half its original concentration and not size. For example, if you have sodium, for example, you have sodium pellets, for example, it has its concentration. Now, the possibility for the concentration of sodium pellet, let us assume that sodium has, let's say sodium has a mass, okay? The mass of sodium, let us say the mass of sodium is, let's say, is 23 grams, okay? And now the concentration of sodium, let's say the concentration is, let's say, 5 grams per mole. Now, it is, if we say half-life, we do not mean that the mass of sodium divided by 2. We say the concentration divided by 2. So if we say half-life, and we are using this 23 divided by 2 to give us, let's say, 11.5, it is wrong. It is rather 5 grams per mole divided by 2 that give us 2.5 grams per mole. That is correct. So that is what, this is what half-life means when you define half-life. So it is the possibility of the concentration of a particular reactant to reduce to half its original concentration and not original size. Now, if that is true, how do we derive the equation for the half-life of a zeroth order? Now we are going to go there straight. Remember that we had said that the zeroth order equation is derived and written as concentration of A is equals to what? Is equals to minus KT plus the concentration of AO. That is what we had derived earlier. In our subsequent, in our earlier class, we had been able to derive this. So you are going to use the zeroth order equation to get at what? To get at your half-life. Now, with this equation, our interest is this. Our interest is not here. This is because this is the original concentration, and this is, of course, the final concentration. So we will do away with this and rather make it 0. So it means that this is 0 is equals to minus KT plus the original concentration. In that case, we are going to certainly make this a subject of the formula. So if we make it a subject of the formula, we are going to bring it this way, and this sign is going to change to negative. So we have minus AO is equals to minus KT. This minus sign will cancel this minus sign and allow the equation to exist as AO equals to what? KT. This means that we are now relating the initial concentration of the reaction of the reactant to what? The rate constant and time. Now, since we are talking of half-life, half-life is always defined as T half. And we are saying that this by half-life definition, we expect that the initial concentration will go half its concentration. That means we'll divide this by 2 and denote this with the correct convention. Now this means that we will say here that let the initial concentration of A be written as A 0 all over 2, and let a time be written as half-life. This is how we write half-life 1 over 2. In this, we are going to substitute this one into this equation. So we substitute this into this equation, and by the implication, it means that this will take this form and this will take the K form. Therefore, we'll now do that. So we now have that A O all over 2 is equals to what? Our K and then the half-life. We substitute the AO over 2 for this and the half-life, which is the T half, for this. Now, at this point, what do we do? So remember, we're looking for the half-life. So if we make T half the result of the formula, it means that we'll now divide the K by this. So this is AO all over 2 divided by K. You see? Now, this equation can be rewritten. It can be rewritten. Now, let us rewrite that equation. If we rewrite that equation, we'll have this equation written as T half is equals to what? AO all over 2 divided by K all over 1. And we can also say AO all over 2 multiplied by 1 all over K. So at this point, we can simply write the half-life equation as half-life is equals to AO all over 2K. This is the half-life equation for what? A zero order reaction. You see how simple it is done. If you follow these steps the way they go, you will see that you can easily be able to do what? Derive the half-life equation for a zero order reaction out of what? Its Rath's law. Today, I'm sure you have learned something also very interesting. Do not forget to like, to share. Do not forget to subscribe at my YouTube channel. Don't forget to also comment.